Hello students, welcome back. In the previous video, we went through the abstract concept of scalar products. We defined it like this. A scalar product is a binary operation that turns two vectors into a scalar that satisfies these four conditions. Number one, symmetric, and number two, positive definite, and then these two put together, bilinear. Or equivalently, number one, symmetric, same as before. Number two, positive definite, again same as before. And then the single condition, bilinear. What's the difference between the two? Here we have additions and scalar multiplications separated out. Here, both were put together as linear combinations. Have you done this before? Yes, twice. Once for subspaces in Module 5 and once for linear maps in Module 7. So here, I'll leave the equivalence to the students. You're doing it for the third time, so you should be able to handle that. So the equivalence between these three conditions, actually the single condition in the middle, and this one, I'll leave the detail to the students. After the definition, we went through some examples. We went through some example. This is the simplest and the most important example, the standard dot product. And this is related to this subsection, which was actually taken from the first module. There, the definition was from the angle, because this originally came from trigonometry class, as a matter of fact. So angles are important there, and some planar geometry. And how do we extend this idea into the n-dimensional case? It's a bit tricky, but that's possible, because you see, if you have any triangle, then a triangle determines a plane. And then in that plane, we can define the angle, and then we can lift it back over to the n-dimensional space. Yeah, it's a bit tricky, but it's possible. So the angle concept makes sense here. But if you go over to this kind of example, then there's no angle, no basis, no coordinates, nothing. Because f and g are from space of continuous functions, and then there's no angle there between those functions, and no picture, no geometry, no bases, and no coordinates, nothing. So we don't have anything like this, like multiply and adding up. No, nothing works. But still, we can do some analysis using scalar products. And yes, you can prove that this actually defines scalar products. How about this example? This example is a bit of a, what should I call, a computation intensive problem. So it's a bit, computation intensive, tedious, and highly unpleasant. But if you do it carefully, it'll work out okay. As a matter of fact, in a little bit more higher point of view, this can be considered as a extension, or what should I call, the generalization of this case. What am I talking about? This example here can be rewritten as a matrix multiplication like this. The row vector times column vector, and do the matrix multiplication, and then we get exactly the same thing as before. But between the row vector and column vector, you can always slip something in. As a matter of fact, excuse me, I made a mistake here. This is n-dimensional, so excuse me. Let me correct this quickly. I should have put some dots here. I forgot about that. Okay. Just a moment. I'm almost there. Okay, there you go. Correction complete. Okay. I can always slip in the identity matrix so that it disappears. And now let's go over to here and then compare this with that. I can slip in a little bit harder matrix in there. So compared with identity matrix, more complicated, but if you select your matrix cleverly, it'll work out. Now, what kind of matrix would qualify here? Do you notice that this matrix is a symmetric matrix? Do you notice? Symmetric with respect to the principal diagonal, and that's necessary. Otherwise, the first condition will not hold. How about the bilinearity condition? It'll always work no matter what kind of matrix you put in here, so that's okay. Perfectly okay. And finally, the hardest of the bunch, the positive definiteness. A matrix, a square matrix, is called positive definite if all of its subdeterminants are strictly positive, if you know what determinants, subdeterminants are. If you don't know it, then never mind. And I'm talking about determinant of this, and the determinant of this, and the determinant of this, and then finally determinant of that. All those has to be strictly positive. If so, then we're gonna have that positive definiteness. And positive definite matrices and those kind of things are important in analysis as well. It is related to a multivariable optimization and stuff, minimum, maximum, and things like that. So matrices belong to linear algebra, yes, but its application is everywhere if you go a little bit higher up. Okay, let's stop here. I shouldn't get a bit too carried away here. I sometimes do that whenever I talk about some upper level analysis. Okay, let's stop here and let's go over to the next topic. Let's resume where we stopped. Let's define the norm using the scalar product. A norm is a square root of scalar product of itself. So please make this analogy. Absolute value of a scalar is this, and for vectors we have something similar. Instead of x times x generating x squared, we have v times v, but this is scalar product. I cannot write v squared, but it does something similar. For scalars, we have single vertical bars, and for vectors, we use double vertical bars. So we use a little bit different notations, but in terms of theory, they do the same thing. Distance from the origin, basically. Now, what about the properties? Well, how about this property, positive definiteness? This is really trivial. I mean, this was defined from square root, positive square root, so always non-negative, duh. And 0 if and only if inside of the square root is 0. So there's nothing to prove here, no detail there. I wrote as if there is some detail so that detail is left to the students, but in reality, no, I take it back. There is no detail, it's just a triviality. No problem there. How about this one? Okay, we can just plug into this definition. Instead of v, plug in CV and then do some computation. No problem there. Let's see. How's this computation? CV, scalar product of CV, and then take those c's out. We have c squared, and take it outside as absolute value, and then that's what we get. No problem there. Pretty simple. What if you prefer to use this triangular bracket notation? Okay, let's do that. CV, comma CV, and then take C out. And then next another C out. Here I changed the order and then took it out. I didn't have to do that, although that makes it slightly more perfect. And then, okay, now that I did it over here, let's not skip a step. Okay, here's the full proof. Okay, which do you like better? This one or that one? To me, about the same, but most of the students I had preferred this one, dot product notation. I'll stick to that. Now, this one, subadditivity. Let's postpone that because this is going to be hard. We're going to do those here. As a matter of fact, it comes over here, and we'll prove it a bit later, probably in a separate video. Let's follow this order. Next topic, unit vector. A unit vector in the direction of v is nothing more than this. Just multiply 1 over norm of v, and then if I take the norm of this, what do we get? That's norm of this and then this is scalar, isn't it? I can always bring it out and times, and what is this? This is always equal to 1. So this is scalar times v, so they're parallel, same direction, and the norm is always 1, and that kind of thing is the unit vector. Unit vector in the direction of v, and it means like that, and then typically we use this hat notation. Of course, if v is a zero vector, it's invalid. Basically, you're dividing by 0, you can't do that. Next concept, orthogonality, and that's something we are going to study in a lot more detail in the next section. And we define the orthogonality as the scalar product turning out to be 0. By the way, if you use this traditional notation of if you use this expression, then v dot w, or norm of v times norm of w times cosine of theta is equal to 0. That means what? That means either one of them is 0 vector, so either v is 0 vector, or w is a 0 vector, or cosine of theta is 0, isn't it? So if this is 0, then v is a 0 vector. If that's 0, then w is a 0 vector. When this is 0, cosine of theta is equal to 0. In other words, theta is right angle. So if you have a concept of angle, then yes, it is perpendicular. You can say that. But if you do not have well-defined concept of angle, and even if you can define it by force, it doesn't make sense geometrically, then it's really pointless doing that. Still, you can define the orthogonality or perpendicularity. You can define it as the scalar product becoming 0. Either you use triangular bracket notation or dot product notation, it doesn't matter. If the scalar product is 0, orthogonal, or vice versa. Orthogonal means scalar product is 0. Perpendicular, again the same deal. There's some further properties of norm that you should remember, and let's see. If you have perpendicular vectors, then we have Pythagorean rule. You see, if v and w are perpendicular, then we form a right triangle. So hypotenuse squared is 1 squared plus the other squared. So yes, we have Pythagorean rule. But if you cannot draw the picture, or if the picture is meaningless, then well, it doesn't make much sense. So let's work it out using the definition of the norm. Let's use the property of scalar product to prove that. Okay, let's start from the left-hand side. And this is v plus w dot v plus w, isn't it? And then the right-hand side is v dot v. This question mark is screwing up this font. Plus w This is basically what you want to prove, because this is the right-hand side. You see, norm square is the scalar product of itself. Scalar product squared is norm squared is scalar product of itself. Norm squared is scalar product of itself. So basically you have to prove this one. And can you do it by foiling out and doing some computation? It's not bad at all. Not bad at all. Just do your computation and you'll see that foiled out the middle part will become just zero vectors because we assumed v and w are perpendicular, orthogonal. So the dot product or the scalar product of v and w, or w and v, it was zero. How about the next parallelogram law? V plus w squared plus v minus w squared is equal to 2 norm of v squared plus 2 norm of w squared. Okay. And I'm not exactly sure. I cannot visualize this parallelogram with this. I mean, this one I can easily visualize. We have perpendicular vectors, so this is hypotenuse squared. So this is Pythagorean, but is this some kind of parallelogram? I don't know, it's a bit hard to see. But algebraically, this is easy. Just norm square is scalar product of itself. Norm square, so scalar product of itself. Again, scalar product of itself, scalar product of itself. Set those up and do your computation. So let's see, from the left-hand side, yeah, scalar product of itself, scalar product of itself. And then let's see, you can fold it out, v dot v, that's norm of v squared, and then v dot w there, and w dot v, okay, middle part, and last, w dot w, that's norm of w squared. Okay, how about this one? Similar deal, foil it. First, v dot v, so that's norm of v squared. And middle part, v dot w, w dot v, we have minus of this scalar product. And finally, last, w dot w, so we have norm squared. Just some algebra. This part, that part cancel each other out, and we have twice of, well, that, and that's precisely what we want is to get. So the proof was simple. I don't know about the importance though. This is really important. This one, we don't really use it very often. Nonetheless, I can write these kind of things in the exams, and that should not cause any kind of trouble to you. Just put those into definition and then work those out. That's about it.